Hi, everyone. I just wanted to check whether you guys can hear me or not. Good. Excellent. So, hi, everyone. My name is Ali Karrech, and I'm one of the academics here in the School of Engineering at the University of Western Australia. My talk today is about the mechanical waves and hydraulically expanded tubes. I just wanted to, so my name is Karrech, actually. It's okay that you mispronounce it. It's pretty common that people mispronounce it, but that's how it is. So this is a work that I did more than 10 years ago, unfortunately, so it's actually not really that new. However, it is still attracting attention, so a lot of my colleagues are still referring to it. So I thought this could be a good addition to the conference. I mean, but again, it's actually pretty old as a work. In addition, I actually did it as part of my master's degree. So you are actually judging the master student that I was many years ago. This presentation contains 3 parts. So the first part is background, a little bit of description of why we dealt with this particular problem. I will also go a little bit through the mathematical formulation of the problem to tell you what are the main assumptions there and what sort of governing equations we use to solve the problem. And then I have a few results and discussion. So this is not a very long presentation, so perhaps it's not going to take 15 minutes, but I will see. So the concept of expanding tubes is pretty straightforward, really. So you take a tube and then you put a tool inside it, and that tool can be a mandrel. We call it a mandrel, basically, and it's usually a rigid tool, relatively rigid. And then you actually either pull it through the tube or pressurize it from the back until it reaches the end. So you can actually see, for example, here, this is a finite element simulation of the process. And you can see, for example, the concentration of stress is there. And on this one here, you see in nature how it is actually done. Let's say on a tube, you just go and run a mandrel through it, and you expand this part here. So the expansion process occurs because of the plasticity of the metal that constitutes the tube. And usually you can go up to 30% or so, depending on what you want to achieve. Now, you do this because of many reasons, especially in the oil and gas industry. So you do it, for example, to reach new reservoirs that are currently not reachable economically. I will explain why is that. And then you can also do it to maintain profitable production from aged wells. This is usually the case when, for example, corrosion can take place in particular regions, or if you have some gas or water that is ingressing inside your casings and things like this. I'll show you, images depicting these phenomena, and then you can also use it for repair. So that's why you would expand tubes like this. Now, one of the dreams that people had at that stage when they started talking about the expandable tubular technology was to achieve monodiameter welds. So this is what I mean by monodiameter welds. So instead of having the telescopic conventional telescopic configuration that you see here, you'd actually go and do an expandable tubular technology, and then you'll actually achieve this sort of monodiameter configuration here. What is the advantage of that? Well, there are many advantages in it, including, for example, the reduction of the amount of steel that will go in these tubes, because as you go up, you'll have to have larger diameters, and when you say large diameter, you mean larger amounts of steel that will have to go in it. But there is also the concrete that you will use to stabilize the whole structure and things like this. So a telescopic configuration would be way more expensive than a monodiameter one. But obviously, that is something that has its own challenges as well. And so that's the spirit of trying to use the solid expandable tubular technology as indicated here. So that's one of the possible applications. Second application is for repair. And also for to shut off water that can come from the surrounding borehole or formation, if you want. So the concept is as follows. For example, if you have this sort of structure here, and with a tube or casing, you're drilling there, but there are areas where that you cannot actually control very well. For example, there are failures there and things like this. So one of the applications would be to consider these tubes and then expend them against the area of where there are problems, that means that you will actually shut off that area. And often you will also use sealings there to make sure that there is no leak of fluids inside the structure. So that's how this works in practice, and that's what people thought they could do with this expandable tube technology. So, and there are two ways to proceed. One way is to apply a fluid. For example, you inject a fluid inside the tube here, and that fluid will drive the tool forward. Okay, so as you do that, you know, the pressure that is here will actually drive the whole thing, and as it is driven through, you know, you'll have expansion occurring. Second possibility is to pull it away. Oops. So pull it away. For example, you'll actually take your mandrel and you pull it mechanically, you know, until it goes through the whole tube. So these are the two possible ways to do it. It's a complex problem, of course, and we studied this from various angles. In fact, we also studied the metal forming aspect of it using the finite element method, but also using analytical solutions. We compared the amount of energies that can go in both cases, and we tried to see what are the optimum friction coefficients, for example, optimum shapes that you could achieve, and things like this. So there's been a lot of work there in terms of understanding how this phenomenon works. But you know, metal forming was also a major problem. Today, I'm not going to be talking about the metal forming aspect, but I would like to talk about the wave propagation after the process ends. Okay, so the situation is that as the mandrel goes through, so it's going to actually expand the whole tube, and then at some stage it will reach the end. And when it reaches the end, vibration can occur. And obviously, you don't want to lose this tube after you have expanded it. And that's really what you want to do, right? So that's the process. So you have the fluid going through it. Sorry. So you have the fluid going through it now until the end. And by the end, basically, the mandrel is going to be popping out. And as it does that, there will be vibration occurring in the tube, etc., due to the fluid that is outside, fluid inside the pipe itself that is now pressurized, and things like this. Okay, so that's basically the problem. This is another view of the This is another view of the structure and how it looks like. So you have the tube, you know, that is represented in black here. In the fluid having a density ρI and a cross section AI and a radius RI, and also the annulus, which is full of fluid in this particular case, just as an assumption. And basically the tube is another view here, longitudinal view. Shows how the tube is fixed from the bottom, of course, because you have to equilibrate the whole system, and you want to understand how the vibration of the tube and the fluid and not fluid occur. All right, so that's what the problem is. Now, in terms of how we formulated this, we made a number of assumptions, as you may imagine, because we wanted to actually solve this analytically. So we assume that the mediums are uniform, which is a fairly good assumption. The formation of and the tube are taken as elastic, isotropic, and impermeable. It is true for the tube to be impermeable, but for the formation, this is not always the case. But we accepted that as a strong assumption. The body forces are ignored here in this case, but we consider the pressure and stresses that are in the tube and the fluid system. Shear stresses due to the fluid viscosities are negligible in the fluid domain, and the steady fluid velocity is low compared to the wave propagation speed. So these are the assumptions. So we actually started from the principles of continuum mechanics. So conservation of mass, for example, in this case. So this is how it looks like in general. One of the possible mistakes that one can make here is to assume that the cross section is constant, and in which case the problem will simplify a lot, and you actually do not get to the point. So here we do not assume that that is the case. We actually assume that, you know, this cross section can actually vary. It means that you know, the radius of the whole domain would actually vary, and so on. So therefore, you have a variation that is there. So this is Gauss theorem, if you want. It also has, you know, so that, or divergence theorem. So both are applicable here in this case. So after you do a little bit of transformation, you actually end up with an equation that has, so this is typical conservation. So you have a variation of the mass with respect to time. And here you have a term that reflects the variation of space, and this term here is actually W is actually the displacement in the axial direction, right? So U here is actually the velocity, and N is just the normal to the domain that you are considering. So this is just pretty much the conservation equation of mass. The same thing, you apply the conservation of momentum here, where you ignore gravity. So if you have gravity, then there will be another term next to this one, which contains the the effect of gravity. But in this case here, we're ignoring gravity, so you only have the inertia term, and then the stress multiplied by the normal to the surface. And that's the whole thing, for the conservation of momentum. And if you manipulate this a little bit in the fluid domain, this term here can also become divergence of sigma. But because we are talking about a fluid that has no viscosity, in this case, the divergence of sigma will just give you a gradient of pressure, right? So that's how we actually end up with this term here. Now, we also apply the considered equation of the fluid. So that's basically bulk modulus equal to this quantity here, derivative of pressure divided by derivative of density, and density as a multiplier here. So after some manipulation, you'll actually get a wave equation, a nice one. But then there is a coupling term here that you wouldn't get if you did not have external things that are happening, and that we will use the variation of cross-section to take into account that coupling between the fluid and between the fluid and the tube, and so on and so forth. Right. So we also wrote the equation of conservation of momentum for the tube. So this is just divergence of sigma, divergence of stress equal to inertia terms here. And then we applied boundary conditions. So these are simple boundary conditions. So the radial stress is equal to the inner pressure. I mean, that's pretty straightforward. And here the radial pressure, the radial stress is also equal to outer pressure in the outer side. We also get the stress equal to sigma 0 originally at time equal to 0, because then the tube was still subjected to the expansion process, right? So at t equals 0, it is under that axial load, and then as soon as the mandrel pops out, that stress will go to 0, right? And that's how we basically try to solve the problem. So these are some terms, important conditions that I wanted to detail there. Applying Hooke's law on this, you get a simple wave equation again, but there you have terms here that ensure the coupling between the different media. All right. So if I summarize, we actually got three equations, wave equations there that are important to take into account. The first one is for the tube. So if you ignore all the coupling terms, then you'll end up with the boring usual equation of wave equation if you want. But then these terms ensure that there is coupling between the inner and outer fluid. So the subscripts P is for the pipe, I for inner tube, I for inner fluid, O for outer fluid. And the same thing applies for the density, for the cross section, and so on and so forth, right? So that's the equation for the tube if you want. With additional terms that are reflecting the coupling. Now it's pretty important to actually know or notice that the coupling wouldn't occur in the absence of Poisson's ratio here. That's pretty straightforward to understand, right? And here, yeah, you have the effect of inner fluid there. And again, we got the inner fluid as a wave equation with coefficients associated with it. And then we also have some terms due to coupling, and the same applies for the outer fluid. Now, the particularity of the outer fluid is that we have here a term that takes into account the formation. So G that you see there is actually the shear coefficient of the formation. As you can see, I'm not actually detailing a lot of the mathematics here, which can be found in the couple of papers that we published on the topic. But I'm just trying to really reflect what are the things that are important to see here. And in particular here, the formation influences the wave equation through this term here. Now, after we obtained all the three equations that are coupled, we tried to solve the system. So we compacted it into various terms. So the first term is looks like a mass matrix. You can see where the mass matrix comes from. It's actually here derivative with respect to time, right? So you have coefficients here, and these would go and populate the mass matrix. As for the second term, it's just derivative with respect to z squared, right? And the coefficient here, E over rho P, E over rho P for every one of them. So this is just the identity matrix multiplied by Young modulus divided by density. And that's pretty much it for for the derivative with respect to z. So the complexity comes from this coupling here that is occurring in the mass matrix. All right, so we assume that there is that the general solution for this will look something like this, and we also consider that there is Rayleigh damping. So the Rayleigh damping is relevant here because we actually wanted to have a damping effect. So we wanted to add that sort of damping effect by having the term C here. I'll explain how that works.
It's already 14 minutes.
Oh, sorry, I have to actually go faster than this then. I'll try to go faster than this slightly. So yeah, so the point here is that K will actually come from this expression here, and C will be just a combination of M and K. That's the usual Rayleigh damping, and now it's a question of actually solving this equation here. So we use a very common approach to do this. So we use the orthogonality of the mode shapes, and then after some mathematical manipulation, we end up with very simple expressions that represent the solution of this particular problem. We also use the boundary conditions in terms of displacement and in terms of pressure inside and outside the tube, and we end up with an interesting solution by identification, by simple identification of all the coefficients that you would obtain in this sort of wave equation if you want. All right, so I'm going to jump now to the solution that we got here. So these are some of the parameters that we used to solve the problem, just common parameters that represent what you would obtain in a well bore. And these are some of the results that we got. For example, here you have the displacement inside or the displacement of the pipe, displacement inside in the inner fluid, displacement in the outer fluid, but also the stresses in the tube, in the inner fluid, and in the outer fluid. You could actually notice that the frequency is higher in the pipe than in the fluids which are inside and outside, but also you will notice that the frequencies are pretty similar for the two fluids that are sitting inside and outside. We also tried to understand the integrity of the tube, so we used an equivalent stress, which is the von Mises equivalent stress, and this allowed us to see how the stress actually, the equivalent stress actually varies with time and space, and you actually notice that this first half, or this area here, is actually the most critical. And it's actually really a moment after the experiment starts that you have the most critical stress that occurs there. So failure may occur near the point where the pipe is being fixed. And that's where we needed to actually strengthen or do something about it. So that's pretty much it for this presentation. So I'll leave you guys with this conclusion to read. But most of the points I mentioned them during my presentation. So I leave it there. It's unfortunate that I actually took more than the allocated time, but if you have questions, please feel free to ask if I'm allowed to answer.
Thank you very much. Very interesting talk. So, do we have any questions? Is there any questions?